I'm going to demonstrate a couple of ways that you can do some debugging of a PIC microcontroller on some of these small devices. So the larger devices, they actually got you can do inline debugging with it in circuit, and you can feed back information to a computer. But with the smaller devices, they don't really allow you to do that, and so there's a couple of methods that you can use, and one of them is to flash an LED with a code to show like a status of how the program's running. And also, because all the PIC microcontrollers have EEPROM in them, this one has 127 bytes of EEPROM, so you can actually log data into the EEPROM, and then I can place it back into the PIC programmer and actually read back any logged data which I had during my test run of my code. So I'm going to actually demonstrate that with this device. So this is a very simple PIC device. It's a 12F629, and it's one of the more basic devices. And so I'm going to put it into my PIC programmer, program it with some example code, and I'll publish this example code on GitHub so you can take it and use it yourself in your own circuits. And then once it's programmed, I'll put it into this test circuit and I'll let it run for a little while, and then I'll put it back into the PIC programmer and I'll bring out the I'll read back the EEPROM and show what's been logged into the EEPROM. Okay, so first of all, I'll put the PIC microcontroller into the programmer, and I'll just run the command to display what's on the PIC microcontroller, just to show that it's empty at the minute. So this is all the memory being read back. So that's the program memory, nothing in it, and here's the data memory, and nothing in the data memory. So if I write to the device, and I'm going to write the program, my debug program, which like I say is on GitHub. Ignore this because I've still got to update my programmer to have a mask for the config stuff. The programming did actually work. That's just erroneous. As you can see down here, it's actually flashing the output codes which I've got in the code. I'll go through the code later and explain it all. What I'll do is I'll actually take it out of the circuit. So I've got to update my programmer as well, so that when the programmer's not powered up, it's actually not powering the device, because these devices can be programmed, can be powered from such low currents. Actually, even when I've got it turned off on the programmer, it still manages to get enough current to run. But I've got it in circuit here, and I've got a PP3 battery which is 9 volts, but I've got a Zener diode, a 2.7 volt Zener diode, and a 1K resistor in series, so I can get 2.7 volts to power the PIC microcontroller. As you can see, it's flashing away. So this is the alert code flashing to show the current status, and it alternates between 1 flash and then 3 flashes, just to demonstrate how you can signal status on an LED, on a single LED, and that only uses up one GPIO line then, and that's this sort of, if you've got a spare GPIO line, or even if most PIC projects probably have an LED on one of the GPIO lines anyway, so you can probably use that. But if I take it out of circuit now, put it back in the programmer, and then I'll just do a display of memory again. So I've got code protection on, which is why all the program memory is showing up as zeros. But you need to have data protection off so that you can view the EEPROM data. And as you can see, what it's doing is it's logging there, and it's got up to this point. So it did that many data logs. It'll fill up the whole of EEPROM if you want to make that many logged values. I've used this to debug an analog to digital signal to make sure to check what value I was getting on the A to D converter. I was logging the values into it, and you can either log single bytes or double bytes or triple bytes. It's best to if you're going to log a double byte, just keep logging double bytes so you know where each one sort of each high and low byte is. Otherwise, if you combine logging single bytes with double bytes, you get lost as to where the single and double bytes actually are. But as you can see, if I go back up to where I check the device is empty, it was all FFs before. But now what I've got is I've got 4 bytes. This is in my example program. You see I've reserved 4 bytes for examples of where I might use actual program EEPROM in my actual program. Then I've got a little code AA and F55 which shows me where the start of the data login is, and it's good to have that because then at least you know clearly where your data login starts, and then data login goes off until either the end of memory or the end of the login that you're making. So I'm just going to go briefly through the code used to do this debugging. First of all, I'll start off just at specifically the lines where the actual debugging code is actually performed. So for the LED flashing, in order to, I'll go for the subroutines in a little while, but this is just the main code. So you load a value up of the flash indicator type, the number of flashes for a particular event, and then you add that to the LED info register which is required, and you do it using an OR, because what you can do is you can add events together. So this LED info indicate is just a single flash, and it's good to have a single flash so that you know that this particular flashing system is working, because if the LED didn't flash at all when there were no events, then you wouldn't know whether the indicator wasn't working or whether it was working and there were just no events. So I'd recommend having like a single flash to show that the indicator's working. And then for each event you want to add, so I've got one I've just called event 1, but you can have multiple different types of event. Then you just add it to the LED info with an OR, and then each one of these would be a power of 2. So this would be a single flash, the indicate, and this would be 2 flashes. So these two together would make 3 flashes. But if you had an event 2, it would be two flashes. Sorry, four flashes. So 1, 2, and 4. So they can combine. So if you had event 1 and 2 and indicate, you get 7 flashes. So you go through your code and you just add these little bits of flashing information at the key points where you want to add, where you want to actually indicate something's happening, and then you call the flash code routine, and that will start the flashes off. But the thing about the LED flashing is the actual code. When I used this, I had to slow my code down so that because the flashes take a certain period of time to do, you want enough time for flashes to occur before you start doing another lot of flash events. So you have to be a little bit careful from that point of view. But it's a very handy and simple way of adding little bits of debugging into your code to say, okay, I know that this event is actually occurring, or I know that this value has actually been reached because I've got this many counts of flashes. So it's simple and quite effective to use. But more effective is this login data. So with this login data, all you do is place a value that you want to be reported to be logged. So for example, in the program which I was logging data for, it was the A to D value from the microcontroller itself. So you'd move that into W, and then you call this log data, and then it takes whatever's in W and it adds it to the EEPROM, writes it to the EEPROM, and that function will automatically increment the address, so that next time you call this function, it automatically writes it to the next address. So all you have to do is load W and then call this, and it will write that data. In here, the test data I'm writing, all I'm doing is incrementing it each time. That's why it counts up by 1 value each time it logs it. So each time it comes around here, it will log another value. I'm doing this in a timer, but I'll now that I've explained the basics of it, I'll go to the top of the code and start explaining from the top of the code how the code works. There's not much code. Like I say, I'm using the 12F629, but this code can be migrated to other PIC microcontrollers quite easily because they've pretty much all got, I think, EEPROM on them, and a GPIO port, which is an output for the flashing LED. I've put a few comments in the code if you go and look at the code as to if you want to migrate it, things to take into consideration, and it's usually that there's the register in banked memory, and so the registers you want to use may be in different banked memory on different microcontrollers. It's just worth checking over that as you migrate it. So I've just defined some constants. So for my LED, I've put it on GP5 for this microcontroller. This time scale is I'm slowing down time 0 so that when I generate the events, and this is what I was saying about flashing the LEDs, that when the events occur, they don't occur so rapidly that I don't get to see the flashes of the events from the previous one. They don't overwrite each other. So that's how I'm slowing down the LED flashing. And these are the definitions of the events that I've got. So LED indicate, that just shows that that the flashing events are occurring. So you get one flash automatically just to show that. And then each event that you want to put in, and you call these events names which are actually relevant to your application, but I've just called them event 1, 2 and 3. And they go up in powers of 2, so you can combine them together, and you can then have multiple events that you can read. I mean, you could just have a series of values from 1 to 32, or well 16, say. When you get too many flashes, it kind of defeats the purpose of the LED, because you can't really count that many. I mean, 16 flashes, I guess you can count reasonably well. So up to 3 events like this, or you just 16 values of different codes that you want to actually read back. Then for the memories, for the RAM registers, I'm just having a couple of registers where I'm because I'm using an interrupt in this demo program. So this is just where I store register values while I'm in the interrupt. These registers are where I scale the time 0 to slow it down so that the LEDs occur a decent period apart. And then for the LED flashing, there's 2 registers you need: LED info and LED flash count. So LED info is where you build up the events that you want to actually indicate, and then when you've built up with all the events that you want to indicate, you call the routine to actually start the flash. And the routine which starts flashing uses this register to to remember how many flashes it's done and how many flashes it needs to still do. And then the log data, all it needs is a RAM register so it recalls where it is in the EEPROM. So there'll be a start point in the EEPROM, which I'll cover later, and then that start point, this is the offset into where it's actually writing the current log of data, so that it writes one from the next location to the next location to the next location. And then this is my test data register. So it's not really relevant for an end program, because you might be taking the data from anywhere, like the A to D port, or some kind of input pins or calculation that you want to actually log. So this is where the microcontroller resets to. I'm just resetting my timer scaling values there. And I'll just skip over for now the interrupt, because I'll just finish going through the rest of the interrupt routine, initialization routine. So I just clear the GPIO port. This is kind of standard stuff for just doing simple initialization. Go to register bank 1, just set the LED to output and all the other pins to input. I'm using the watchdog timer. I just do it by default. You don't really need a watchdog timer, but this is just pre-scaling watchdog timer, so it's a nice big value. And I'm setting up so that I've got time 1 interrupts, and then I'm going back to register bank 0. I'm set up time 0 2. I'm enabling interrupts and enabling interrupts for time 0, and then clearing any previous interrupt flags so that they will trigger. And then I'm setting up timer 1. Then these are this is, you need to initialize the values so you don't get any spurious values at the start of the program. So I'm initializing the LED and data login registers which I'm using, and this separately my test data. And the actual main routine on here is just an infinite loop. So it actually doesn't, the actual program itself doesn't do anything. Everything's done on interrupts on timers for this example. These are the 2 functions which I will cover in a second. What I'll do is I'll just jump back to the interrupt routine and cover what happens in the interrupt routine. And the reason I had to jump around is because the interrupt routine always sits at address 4. So this is what happens in the interrupt handle. This is standard interrupt stuff. It's just storing the W register and the status register so you don't mess them up when you return from interrupt, and it can continue as it was, making sure it's in register bank 0. Okay, so timer 0 I'm using as my test harness. So this isn't to do with actual the code that you might want to put into your program. This is just exercising the login, data login. I'm just using this to periodically exercise the data login. And like I say, I'm scaling it to a value, the timer to a value, so that it occurs, every couple of seconds, so that it's slow enough that I can actually get the LED indications to happen between actually invoking them. And then this is the bit of code which I covered at the very start. So I'm flagging a single flash on the indicators to show that the actual indicator is working, and then I'm just doing a test on the test data, because the test data is going to increment every time it comes into this timer. And I'm saying that if bit 0 is set, then what we want to do is we want to just do this LED indicate. But if it's not, if bit 0 is reset, then I'm going to add this second event. So that's why when you saw the actual program running, you'd see a single flash, then 3 flashes. So it comes around, it does that, and then it comes around again and it'll do the event 1 as well. Then it go back to single flash, double flash. So that's just showing that how you can change the LED event that you want to actually occur when they occur. And then when I've selected what events I want to flash, I just call the flash function, and then it will handle doing however many flashes I want to do. And again, this is just the logging the data, which I covered at the start of this explanation. So it's just logging the test data and then incrementing the test data. And so next time it comes around, it will log one value higher. And then that's the end of timer 0. But then it goes into timer 1, and this is actually used to run the flashing of the LED for the flash debugging. So if you were already using timer 1, then maybe you could use a timer which was free for doing it, or you can combine it into timer code that you've already got if you don't have any spare timers. And all it does is it says, are there any flashes still to be done? If not, then don't worry, we don't have to do any flashes. But if there are, then it decides if the LED is already on or not, and if it's not on, so if it is on, then it switches the LED off, and it decrements the number of flashes it needs to do. And if it's not on, it turns the LED on. So it handles doing a flash and counting down how many flashes it needs to do left. And the code is as simple as that for doing LED flashes. And then it comes to the end of the interrupt routine, and it's just this bit is standard code in the interrupt routine to restore the status register and the W register. So that just leaves the actual functions themselves to explain. So there's 2 functions, one for the LED flashing, and this is to initiate a set of flashes. So you've loaded up in the LED info register the actual number of flashes you want to do. And when it comes in here, make sure the LED is switched off to start with, so you get a nice clear number of counts. If anything's switched on, the LED on by mistake in between, you need to make sure it's switched off so you can count exactly how many are happening. Also, it makes sure that the timer starts off from 0. So the first flash is a consistent full amount of time, because you don't want the timer to almost be at switch in time, and then the first flash is so short that you don't really notice it. So this makes sure that the flash happens for the full time it's supposed to do on the first flash. Then it gets the number of flashes that you've told it you want, and it puts them into the flash count so that the interrupt can then flash the appropriate number of LED flashes, and then it clears the LED info 1 so you can start registering up your next lot of flashes to occur on the next event that you want to show what's occurred. And then there's the log data function, and this it looks longer than it really should be. So most of the prom stuff occurs in this particular microcontroller in register bank 1. that may vary from microcontroller to microcontroller, so it's worth, if you can migrate this code to a different microcontroller, go through and check where all of these registers are supposed to be, because you need to select the correct banks to make sure you use the right registers. So whatever's in the W register when coming into this routine gets stored as the actual data to be stored in EEPROM. We get the start address in the EEPROM where we're going to start from. I'll explain that in just a second after this routine. But basically, so in your program, you probably want to use some of the EEPROM locations for your program. So at the end of those locations, you put this label in so it knows that it should only start logging the data into those later memory locations, so it doesn't overwrite your actual variables. And then we add to that start position the offset position where we are currently writing the data to, and it stores that in the register to actually write to the address of the EEPROM to write to for the microcontroller. And then the reason it uses move F to F is that this move WF doesn't affect any registers, but if we move F to F, we can check the zero we can check for a zero value, because if it's a zero value, then we've reached the end of the EEPROM memory, and we don't want to start overwriting stuff at the beginning of the EEPROM memory, because it's probably stuff you're using in your program, and we shouldn't overwrite that, so it would cause problems with the program otherwise. So once we get to the end of the EEPROM, we don't bother writing anymore to the EEPROM, the login stops. So then we just go through the standard routine which you use to write to an EEPROM address. So you set the flag to say we want to write to EEPROM. For this period, we disable interrupts because we can't have interrupts at this point. Then we send the code to the microcontroller to say that we want to actually write to EEPROM. So this is like an unlocking code to make sure that we don't accidentally write to it when we don't want to. And then we say initiate the write process to the microcontroller. After that, we can enable interrupts again. And then this is a loop here where we wait for the end of the write to EEPROM process to complete. So this is a tight loop. So in other circumstances, you might want to make this interrupt dependent, but we'll just keep it in a tight loop. It keeps it simple here. And then afterwards, you make sure that writes to EEPROM are disabled again. Update the offset into the EEPROM where we'll actually log into. So the next time it comes in, it will write to the next address and won't overwrite what we've just written. And then it will continue until it gets to the end of EEPROM. And then we make sure that it's at register bank 0 again before returning from this function, so that it can resume the rest of the program in the correct register bank. Okay, and then this is just where define the EEPROM which we have. So this is EEPROM memory, and the first 4 bytes I've just got an example in this particular thing to show that demonstrate it won't overwrite them, and we have got 4 zeros. Just as an example, this is data that we might be using in our program. And then I've put an AA and a 5.5 code into EEPROM memory, and this is so that when you actually examine the EEPROM memory after you've logged stuff, it's easy to find the position where you actually started logging, because it'll be after the AA and 5.5. Otherwise, it might be a bit confusing as to where the login started. You can change those values to any values you want if you've got favorite values for identifying the start of login point. And then this is that label I described earlier. This is the offset into EEPROM where it's going to start login to, and it's going to start at offset 0, and then it'll just keep going through the memory until it gets to the end of memory, but it won't wrap around to the beginning again. And that's a brief explanation as to how it works.